Okay, my last session, which was supposed to be on slides 5, 6, and 7, crashed right before I got to the slide 7, which is the applications of ultrasound. I'm not going to go through that. There's a good description of it on pages 458 and 459. I gave you a bit of application from how we used to use it at Southwest Research. I myself have used ultrasonic probes looking for um, uh, different aggregate in concrete slabs. So it is used quite a bit in non-destructive testing, and it is used in the medical field. So if you're going to take your MCAT, I don't know that they're going to have any type of questions like that, but it's probably certainly worth reading. If you're not taking the MCAT, I'm not going to hold you responsible for anything. So we're going to go on to the next section, the speed of sound, which is section 14.3. Let's move this over and get going. The speed of sound, the speed of a sound wave in a fluid depends on two things: the fluid's compressibility and inertia. If the fluid has a bulk modulus B and an equilibrium density rho, the speed of sound in the fluid is given here. This equation also holds true for a gas. As you remember, the bulk modulus is defined as the ratio of the change in pressure, delta P, to the resulting fractional change in volume. There we go. The resulting fractional change in volume. B is always positive because an increase in pressure results in a decrease in volume. That means the ratio delta P over delta V is always negative. In general, the wave speed depends on an elastic property of the medium and on the inertial property of the medium. In fact, the speed of all mechanical waves follows an expression in the general form shown. Here are the equations for the speed of transverse waves on a string and the speed of longitudinal wave in a rod. Where y is the Young's modulus of the solid and rho is its density. Note that this expression is only valid for a thin solid rod, even though in the problem, one of the example problems I give you on Earth, the longitudinal wave in an earthquake does use this same formula. It's not a long, thin rod, but that's okay. Now here is a table. This table lists the speeds of sound in various media. As you can see, the speed of sound is much higher in solids than in gases. This is because the molecules in a solid interact more strongly with each other than do molecules in a gas. Imagine striking a long steel rail with a hammer. Two sound waves are produced, one moving through the rail and a slower wave moving through the air. If someone pressed an ear against the rail, they would first hear the faster sound moving through the rail, then the sound moving through air. In general, sound travels faster through solids than liquids and faster through liquids than gases, although there are exceptions. Okay, we're going through slide 10.